Calculation of lift and drag coefficients plays a crucial role in aerodynamic design. Hello, I'm Armin. In this video, I'll show you how to calculate the lift and drag coefficients and how to plot the velocity and Yplus contours to ensure accurate simulation results. Before diving into the calculations, let's briefly go over the model setup. Airfoils are streamlined bodies designed to generate aerodynamic forces when exposed to an airflow. When air passes over an airfoil, the velocity distribution around its surface creates a pressure difference between the upper and lower surfaces. This pressure differential produces a net upward force known as lift, which acts perpendicular to the relative airflow. In contrast, drag is the aerodynamic resistance force that acts parallel and opposite to the direction of motion. A key parameter influencing lift and drag is the angle of attack, defined as the angle between the chord line of the airfoil and the oncoming airflow. At small angles of attack, lift increases approximately linearly with the angle, in accordance with thin airfoil theory. The lift and drag coefficients are fundamental non-dimensional parameters used to quantify aerodynamic performance. CL and CD represent the lift and drag coefficients. Rho is the fluid density, V is the free stream velocity, and A is the reference area, typically the planform area of the airfoil. In this tutorial, a two-dimensional compressible air model is used, where air is treated as an ideal gas. The upstream domain shape, whether curved or flat, has no significant influence on the results. Therefore, a horizontal inlet boundary can be used. The boundary conditions are defined as follows: a velocity inlet at the upstream, upper, and below boundary, a pressure outlet at the downstream end, and wall boundaries assigned to the airfoil surfaces. The computational mesh is divided into three zones to effectively capture the flow gradients. The mesh is extra fine near the airfoil surface, fine in the intermediate region, and medium in the far field domain. The solver is set to steady state using the coupled scheme for pressure-velocity coupling. For spatial discretization, a second-order upwind scheme is applied to achieve higher accuracy in the solution. After the simulation, we'll first display the velocity contour to visualize the flow regime around the airfoil. Next, we'll examine the Yplus distribution along the airfoil surface to verify mesh quality and near-wall resolution. A proper Yplus ensures accurate turbulence modeling and reliable lift and drag predictions. Finally, we'll generate plots of the lift and drag coefficients to evaluate the aerodynamic performance. Now let's start modeling. The Airfoil Tools website provides a large database of NACA airfoils. In the search section, I'll select the NACA 4-digit series to browse some well-known models. Here, we can access the lift coefficient, drag coefficient, and the airfoil cross-section coordinates. For this tutorial, I'll choose the NACA 0012. At the top of the page, you can see the airfoil shape, and in this small window, the coordinate data is listed. The site also provides plots of lift coefficient versus angle of attack, drag coefficient versus angle of attack, and the lift-to-drag ratio. These curves are very useful when we want to validate our CFD model later. Now, I want to import the coordinates into ANSYS SpaceClaim to create the geometry. To do that, I'll copy the XY coordinate data into Notepad and save it as a text file. I'll name the file NACA0012.txt and then click the Save button to store it in the correct format. Before importing, we need to prepare the file in Excel. I'll open the text file in Excel. When you open the text file, the text import wizard will appear. Click Next, enable the space delimiter, then click Next and Finish. Now the coordinates are arranged in columns. The first row is incorrect, so I'll replace it with zeros in columns B and C. As I mentioned earlier, we also need to add a 1 in column A. Just type 1 in the first cell, then double-click the corner to fill the entire column automatically. When reviewing the data, you'll notice that row 67 is empty. We'll leave it blank. And then in row 68, I'll type 1 again and double-click to fill column A. Everything is now ready to import into SpaceClaim, and I'll leave the empty row as it is. I'll save the file and then close Excel to finalize the preparation. Now let's begin setting up the simulation. I'll double-click on Fluid Flow, Fluent. Since our airfoil geometry is 2D, I'll go to Geometry, open the Properties, and set the analysis type to 2D. Next, we'll create the geometry. Right-click on Geometry and select New SpaceClaim Geometry. Of course, you could also use Design Modeler or Discovery, but for this tutorial, we'll continue in SpaceClaim. Once inside SpaceClaim, I want to set up the work plane properly. I'll click on the Sketch Plane button, choose the XY plane, and then click Plan View for a perpendicular view. Since the NACA coordinate file is unitless, we need to define the correct units before importing. Navigate to the File tab, click SpaceClaim Options, and under the Units tab, change length from millimeters to meters. Click OK to confirm. Now we can import the airfoil. I'll go to File, Open, change the file type to All Files, select the NACA 0012 text file, and click Open. The airfoil profile is now imported. Click End Sketch Editing to see the profile. As you can see, the trailing edge is open because row 67 in the text file was left empty. To fix it, navigate to the Design tab, click Sketch Mode, and select the XY plane. Using the Line tool, I'll connect the two endpoints of the trailing edge. After that, click End Sketch Editing. Now we have a closed curve. Next, we need to create a surface from the curve. I'll select the curve and click Fill from the Design tab. Here you are. The airfoil cross-section surface is complete. Press Escape. In the structure tree, you'll see a surface, a sketch plane, and a curve folder. Since we only need the surface, I'll delete the curve folder and the sketch plane. Let's check the chord length to confirm the scale. Navigate to the Measure tab and select Measure. Hold Ctrl and select the leading and trailing edge points. The chord length reads 1000 millimeters, which is correct. Now we need to define the environment domain around the airfoil. I'll go to the Sketch tab, select the 3-point arc tool, and draw a 180-degree arc with a radius of 11 meters on the XY plane. Next, I'll draw the downstream region on the right side of the arc. I'll select the Line tool from the Sketch tab and draw a horizontal line. I'll enter an angle of 90 degrees and a length of 14,000 millimeters to define the rectangle for the wake region. I'll continue drawing to form a rectangle. To position the domain correctly, I'll switch to the Dimension tool. I'll select the arc and confirm its radius as 11,000 millimeters. I'll select the horizontal upper line and confirm that the dimension is correct. Then I'll select the horizontal line and the x-axis and set the spacing also to 11,000 millimeters. Everything looks good. Click End Sketch Editing and press Escape to exit. As you can see, in the structure tree, there are two domains, the environment and the airfoil cross-section. Our next step is to subtract the airfoil cross-section from the environment domain. Before doing that, let's first apply an angle of attack to the airfoil. I'll select the airfoil surface, go to the Design tab, choose Move, and rotate it by 5 degrees. Then I'll press Enter to confirm and Escape to exit the Move tool. Now we can subtract the airfoil from the domain using the Project operator. From the Design tab, I'll click Project, select the airfoil surface, then choose Select Target Faces and pick the Environment surface. Finally, I'll confirm with the green check mark and press Escape. If I now hide the airfoil, you can see that the airfoil cross-section has been projected onto the environment domain. I'll select this projected surface and press Delete. There you go. Since we don't need the original airfoil surface in the simulation, I'll right-click on it and choose Suppress. In the final step, we need to assign names to each boundary. I'll select the airfoil wall, go to the Groups tab, click Create NS, and name it Walls, then press Enter. The right side of the domain is the outlet, so I'll select it, click Create NS, name it Outlet, and press Enter. Finally, the top, bottom, and left boundaries represent the inlet. I'll group them together, click Create NS, and name them Inlet. Everything is now set up. Let's quickly review the names. Airfoil is wall, right side is outlet, and the remaining sides are inlet. Everything looks correct, and we can now proceed to meshing, but before that, I'd like to add 2 smaller zones so we can apply a refined mesh around the airfoil. To do this, I'll go to the Design tab, enable Sketch mode, and select the XY plane. From the Sketch tab, I'll choose Rectangle and draw a box around the airfoil. Let's say 6 meters by 5 meters. I need to adjust its position, so I'll use the Dimension tool to relocate the rectangle. First, I'll click on the left edge and confirm the dimension. Then I'll select the x-axis and the top edge and set the offset to 2500 millimeters. Since the wake region requires a larger refinement, I'll again use the Dimension tool and set the distance between the left and right edges of the rectangle to 8000 millimeters. That should be enough. Press Enter, and now the rectangle is in the correct position. I'll click End Sketch Editing and press Escape. In the structure tree, we now have 3 surfaces. Next, we need to project this rectangle onto the air domain. I'll select the Project tool, click on the rectangle, choose Select Target Faces, pick the air domain, and confirm with the green check mark. Press Escape, then delete the original surface. As you can see, the domain is now sectioned, which allows us to apply a smaller mesh around the airfoil. Let's repeat this process to create an even smaller refinement zone. I'll go back into Sketch mode, click on the domain, choose Rectangle, and draw a smaller box, for example 3 meters by 2 meters. Using the Dimension tool, I'll confirm the values. Then I'll select the x-axis and the upper edge and set the offset to 1 meter. Finally, I'll click End Sketch Editing and press Escape. Now I'll project this smaller rectangle onto the air domain. Again, I'll click the Project tool, select the rectangle, choose Select Target Faces, pick the larger rectangle, and confirm with the green check mark. Press Escape and delete the original surface. Here you are. Now we have 3 nested zones inside the air domain. This setup lets us apply 3 different mesh densities: extra fine near the airfoil, fine in the intermediate zone, and medium in the outer domain. Let's quickly recheck the named selections. Everything is correctly defined. Now we can save the geometry and close SpaceClaim. The geometry has been prepared. Now let's move on to the mesh generation. I'll double-click on Mesh and wait for the environment to open. We are now in the meshing environment. Before making adjustments, let's generate the default mesh to see how it looks. I'll right-click on Mesh and select Generate Mesh. As you can see, the default mesh is far too coarse. Let's change the element size from the default value to 200 mm and update it again. This size looks better, but if I zoom in, you'll notice that the mesh around the airfoil is still too coarse. That's exactly why I sectioned the environment earlier. Let's now add a local sizing control. I'll right-click on Mesh, go to Insert, and select Sizing. I'll pick the larger rectangle and click Apply. For this zone, I'll specify an element size of 50 mm and regenerate the mesh. Here you are. This finer mesh can capture the wake region more accurately. Next, let's refine the smaller rectangle. Again, I'll right-click on Mesh, go to Insert, select Sizing, then pick the smaller rectangle and click Apply. I'll set the element size to 10 mm and regenerate the mesh. Now you can see the mesh around the airfoil is much finer. However, we still need even more refinement directly along the airfoil walls. I'll use edge sizing to improve it. I'll right-click on Mesh, choose Insert, Sizing, and switch to the Edge selector. Then I'll double-click on the airfoil edges to select them all and click Apply. For these edges, I'll specify an element size of 6 mm. In the Capture Curvature option, I'll change Yes to No. Then I'll set the behavior from soft to hard. This ensures that the edge sizing will override the face sizing from the previous step. Let's regenerate the mesh. Now you can see that 2 boundary layers have been generated. However, 2 layers are not sufficient for our simulation. We need to increase the maximum layer from 2 to 10 and generate the mesh again. Here you are. The mesh has been generated and it looks much more suitable for our simulation. It's important to note that the boundary layer mesh directly influences the Y+ value in the simulation. Remember, Y+ depends on the flow velocity. So if the stream velocity increases, the first layer thickness must be decreased to maintain proper turbulence resolution. Everything is now correct. I'll close the mesh module. If you see the lightning icon in the mesh cell, that means it's outdated. Simply right-click on Mesh and select Update. The next step is to set up the simulation. I'll double-click on the Setup cell. The Fluent Launcher window now appears. I'll enable Double Precision to increase the accuracy, and in the processing options, I'll type 8 processors. Of course, this number depends on your computer's CPU. Finally, I'll click on Start. We are now in the Setup module. I won't change anything under the General options. This will be a steady-state analysis using the pressure-based solver in 2D. Now let's configure the models. I'll expand the Models section and double-click on Viscous Model. Here we can choose the turbulence formulation. For this case, we'll use the K-omega SST model, which is suitable for both internal and external aerodynamic flows. Of course, we could also use the inviscid model with incompressible air, but this assumption is not accurate when calculating lift and drag coefficients. So I'll leave the model as K-omega SST and close the window. Next, let's prepare the material properties. I'll expand the Materials section and double-click on Air from the Fluids list. By default, the air density is set to constant. To increase accuracy for compressible flows, I'll change the density from constant to ideal gas, then click Change/Create. Since air becomes compressible at speeds greater than Mach 0.3, this setting is necessary. Everything looks good, so I'll close the Materials window. Now I want to specify the boundary conditions. I'll expand the Boundaries panel, and here we see 4: walls, outlet, internal, and inlet. Let's start with the inlet. By default, it is defined as a velocity inlet. I'll double-click on it to open the settings. In this section, we need to specify the velocity magnitude. Keep in mind that lift and drag forces depend on the Reynolds number, which in turn depends on velocity. So if I change the velocity, the lift and drag values will also shift slightly. In the graphics window, you can see blue arrows indicating the direction of the inlet velocity. I want the flow velocity to be only in the x direction. To do this, I'll change the velocity specification method from normal to boundary to components, and then specify the velocity in the x direction. For example, let's enter 10 meters per second. Note that the velocity is strictly along the x-axis, even on the top and bottom boundaries. I'll click Apply and then Close. Now let's expand the outlet. By default, it is set up as a pressure outlet, which is fine for this simulation. However, if we use velocity defined in terms of Mach number, then both the inlet and outlet should be set as pressure far field. In other words, when working with Mach-based flow conditions, inlet and outlet must be pressure far field boundaries. Since in this tutorial I'm using velocity in meters per second, I'll leave the outlet as pressure outlet. Everything looks correct. Let's move on to the solution methods. I'll expand methods, and we can see that the scheme is set to coupled, which works well for both compressible and incompressible flows. All of the discretizations are already set to second order, which is suitable for this case. If you're simulating at very high velocities, it's often recommended to enable the high-order term relaxation option to improve the stability of the solution. Let's move on to the solution controls. There's no need to change the defaults here, so I'll leave them as they are and continue to the initialization section. By default, hybrid initialization is selected, and I'll keep it that way. This method provides a good initial guess for the flow field. I'll click on Initialize. To further speed up convergence, it's often better to enable FMG initialization. I'll click on FMG and a panel opens. But before using it, let's first visualize the effect of the default hybrid initialization. I'll expand Graphics, right-click on Contours and select New. I'll rename the contour to Velocity, change the contour variable from pressure to velocity magnitude, and then click Save Display. Finally, I'll close the window. As you can see, this is the velocity field based on the hybrid initialization values. Now let's apply FMG initialization. I'll click on FMG again and then click on Calculate. After just 5 steps, the initialization is complete. Let's check the improvement. I'll double-click on the velocity contour, click Save Display, and here you are. You can clearly see that the velocity field has been significantly improved compared to the hybrid initialization. Now I'll navigate to Run Calculation. Let's specify 500 iterations and click Calculate. The solution converges very quickly since our boundary conditions are well defined. I'll click OK and check the residuals. As you can see, the solution has converged in about 30 iterations. To increase accuracy, we can tighten the residual monitors. I'll expand the monitors panel, double-click on residuals, and decrease the absolute criteria by 1 order of magnitude, simply by adding a 0. Note that we don't need to run initialization again, otherwise it would restart the solution from the beginning. I'll click on Compute to proceed with the solution. Here you are. The solution is updated quickly with stricter convergence criteria. Before moving on to calculate lift and drag coefficients, we need to check the wall Yplus values. I'll right-click on Contours, select New, rename the contour to Yplus, and change the variable to Turbulence and select Yplus. Then I'll click Save Display and close the window. As you can see, the Yplus around the leading edge is above 21, which is relatively high. We need to reduce the Yplus value to be between 1 and 5, so I'll close the setup interface and save the solution. To refine the boundary layer mesh, I'll double-click on the mesh cell. In this step, we need to decrease the first layer height of the inflation mesh. I'll expand the mesh tree and select Inflation. Currently, the first layer height is 0.6 millimeters. I'd like to divide that by 5, which should roughly reduce the Yplus value by the same factor, so I'll enter 0.12 millimeters and press Enter. It's also better to make the smaller regions slightly finer to avoid high aspect ratios in the mesh. I'll click on Face Sizing 2 and change the element size from 10 to 6 millimeters, then press Enter. Next, I'll go to Edge Sizing and reduce the size from 6 to 4 millimeters. Now the aspect ratio of the mesh should be much more reasonable. I'll right-click on Mesh and select Generate Mesh. Once the mesh generation is complete, let's check the number of elements from the statistics. As you can see, we now have about 207,000 elements. Everything looks good, so I'll close the mesh environment. Before proceeding, I'll update the mesh again by right-clicking on the mesh cell and choosing Update. Now let's go back to the solution by double-clicking on the solution cell. I'll go directly to the solution setup because I don't want to redefine all the boundary conditions from scratch. Inside the setup environment, let's quickly review the boundary conditions. I'll expand the inlet and double-click on the velocity inlet. As you can see, the velocity settings are the same as before, so we can go straight to initialization. I'll click on Initialize, and again, I'll enable FMG initialization to accelerate convergence. Everything is ready, but before we start the calculation, let's set up the lift and drag coefficient reports. We can monitor the coefficients during the solution process. I'll right-click on Report Definitions, select New, and choose Drag. The drag coefficient option is selected by default. I'll select Walls from the zone list, rename it to CD, and click OK. Next, I'll right-click on Report Definitions again, go to New, Force Report, and select Lift. I'll choose Walls as the zone, rename it to CL, and click OK to confirm. One final step before solving. We need to check the reference values to ensure the coefficients are calculated correctly. I'll double-click on Reference Values. Note that changing these doesn't affect the actual simulation results, it only affects how the coefficients are computed. From the Compute From drop-down, I'll select Inlet, and you can see that the density and velocity values have been updated automatically. This ensures that the lift and drag coefficients are calculated using the correct reference conditions. Now we're ready to run the simulation. I'll go to Run Calculation and click Calculate. The solution converges smoothly. After about 40 iterations, the residuals drop and the solution is complete. Let's check the results. The drag coefficient is approximately 0.01, and the lift coefficient is around 0.52. To validate these results, let's compare them with data from the Airfoil Tools website. As you can see, the lift and drag coefficients at a 5-degree angle of attack fall within the same range as our results. The plotted data correspond to different Reynolds numbers, which can be adjusted as needed for comparison. Now, let's visualize the flow field. I'll expand Graphics, open Contours, double-click on Velocity, and click Save Display. This is the velocity contour around the airfoil with our refined mesh. Finally, let's recheck the Yplus distribution. I'll right-click on Contours, select New, change the contour variable from Velocity to Turbulence Yplus. Select the wall surfaces and click Save Display. As you can see, the Yplus values near the leading edge are around 5 and decrease gradually along the surface, which is within the ideal range. This confirms that our mesh and wall treatment are suitable, and the lift and drag coefficients are now accurate and reliable. If you need highly accurate results, use a Yplus value close to 1. The tutorial ends here. Thank you for watching.